Balliol College have kindly invited me here to talk to you today about some of the research that I have done to do with sea ice fracturing and climate change. Um, so thank you all for attending. We're going to have quite a lot of interactive activities, so there will be opportunities to ask questions and put things in the chat. So please try to get as involved as you can. So today is all about learning something a bit new that builds on some concepts you already know from your A-level studies. So a little bit about me to start off with, so I'm not some random person just talking at you for an hour. So I grew up in the West Midlands. My name is Grace. Yeah, I did my GCSEs and then my A-levels, just like you're doing now. So I'm from the UK. And then I continued to Durham University, where I got my first class integrated master's degree in physics and maths. And then in between my third and fourth year, I did an internship with Dove Marine Laboratory up in Newcastle, and I investigated the concentration of microplastics in samples brought back from the Southern Ocean. Then in my fourth year, I undertook a master's research project on the topic of sea ice fracture mechanics, and that's what I'm going to talk to you about today. And since finishing my degree at Durham, I taught GCSE maths in a school and I travelled, and now I am pursuing my PhD at Oxford University in Wind and Marine Energy Centre for Doctoral Training. So I research the interactions between wind turbines and the atmosphere. I've also recently become president of Oxford's Women in Engineering Network, which is very rewarding and includes lots of fun and insightful events into the world of engineering. I also currently tutor a range of GCSE and A-level students, and I really like working to help teach people and showcase how amazing and interesting physics, maths, and engineering can be. So let's have a look at the motivation behind the research, which is climate change. So most scientific papers and presentations start with a motivation behind why the research undertaken is topical, important, and impactful. So we're going to do just that and look at the motivation behind studying the fracture mechanics of sea ice. So the motivation behind looking at sea ice in particular is it's important for not only its response to climate change, which causes a lot of environmental damage, but also for what it tells us about the rate of global warming itself. So the response of it to climate change, and also how it tells us the indication of how bad the climate change is at the moment. So let's have like a little bit of a climate change quiz. I'm gonna try and get the poll function to work. So if I just put in options 1, 2, 3, and 4 on the poll, and your question is this. Globally, which of the following economic sectors emits the largest percentage of greenhouse gas emissions? So let's have a see if this works. So it's just sharing the poll. So let's have a go at which section it is. Okay, good. Some responses coming in. I'll wait for just a few more. Okay, so we've got 7 responses now. The majority think it is 3, industry. It is actually number 4, electric power. So the electric and heat production sector accounted for 34% of 2019 global greenhouse gas emissions, followed behind by the industry sector, which is very close, accounting for 24%. So while emissions are still on the rise, the rate of increase for energy and industry has slowed between 2009 and 2019. And let's have another go. So let me just set up a second poll. So what was agreed to in that came out of COP21 held in Paris in 2015, and if I put this in the poll, if you just select option 1, 2, 3, or 4, so do we know what came out of the Paris Agreement? Okay, good. We've got quite a lot of responses for this one. Okay, so 100% of people have said option number 2, which is correct. So it's to keep global temperature rise well below 2 degrees Celsius pre-industrial levels, which means that we have a certain level of temperature at industrial, like just before industrial levels, and it's about keeping that well below 2 degrees increase from what it was before. So the Paris Agreement is an international treaty on climate change. It aims to keep the overall increase in global temperatures below 2 degrees Celsius, with the hope of limiting it to 1.5 degrees Celsius. Scientists believe that these are the largest increases in global temperature that we could experience without causing catastrophic change to the Earth's climate. So the average temperature of the Earth is rising due to a process known as global warming, which hopefully you'll have all come across. Since the late 19th century, the planet has warmed by about 1.1 degrees to 1.3 degrees, with the last decade being the hottest on record. So on the screen, you can see a graph showing this phenomenon, with the y-axis being frequency of occurrence. So if I just get my pointer up, the y-axis is frequency of occurrence, and the x-axis is temperature, going from extremely cold to extremely hot. And then here it displays the years, the number of years in between. So 1951 to 1980 is one time period, for example. So if I just flick through, you can see this is changing the number of years. And we can see quite devastatingly that we're shifting this graph to the right, which means that we're moving towards hotter and hotter temperatures, and that's extremely concerning. Another figure here is just to show how hot we are making the planet. Most areas of the planet you can see are in yellow, red, or orange, which means that we have between 0.5 and 4 degrees of warming in these areas. So the overall trend in the planet is that of global warming. And even the places here, which show that there's a decrease in temperature, are actually caused by the effects of climate change. For example, here, ice might be melting and decreasing the temperature of water in those regions. So even though it looks like this area is cooler, it's actually because there's changes in the ice that's melted because of global warming, or changes in wind patterns caused by global warming as well. So here are two figures taken from a BBC News report. The figure on the left shows that the year 2024, so obviously last year, was the world's hottest on record, with climate change mainly responsible for the high temperatures. It was also the first calendar year to surpass this 1.5 degrees critical, which was talked about earlier for the Paris Agreement. So that's actually quite worrying that we're now surpassing that 1.5 degrees that we were trying so hard to not surpass. So the climate has changed naturally throughout the Earth's history, but natural causes physically cannot explain the particularly rapid warming seen over the last century. Now, in the graph on the right, so now the graph is going from 800,000 years ago to today, whereas the graph on the left was only 1940 to 2020. We can see, I think even more alarmingly, this hockey stick shaped graph, which shows that we've got random fluctuations in the levels of carbon dioxide, which change. And here we can quite clearly see that that is extreme in comparison to any time in the last 800,000 years. So that's a critical point. So we're at a critical point now. So to help keep global warming to the 1.5 degree limit agreed in Paris, CO2 emissions need to be at net zero by 2050. This means reducing greenhouse gas emissions as much as possible, as well. Now we're at the stage where we actually need to be actively removing any remaining emissions from the atmosphere. So not only do we need to limit the amount that we're currently putting in, we need to remove some of the carbon dioxide and greenhouse gases that are already there. So most countries have or are considering net zero targets. However, greenhouse gas levels are still rising too quickly, and the world is likely to warm beyond 1.5 degrees. However, it's not all bad. There has been progress in some areas, such as the growth of renewable energy and electric vehicles. So we definitely have hope to rectify this situation, and hopefully with lots of great research and industry innovations, we should be able to tackle this problem if we act quickly and with drastic measures. So let's have another poll. as part of the climate change quiz. Let me just put these options in. Okay, so if you want to put in what you think the greenhouse effect is. Okay, awesome. It looks like people know what the greenhouse effect is, which is very positive. So it's option number 3, when the gases in our atmosphere trap heat and block it from escaping our planet. So the Earth receives solar radiation from the sun. Passing through the atmosphere, some radiation is absorbed by the Earth, while some is reflected back into space. When the exchange of incoming and outgoing radiation occurs, some of the radiation becomes trapped by gases in the atmosphere, and this creates a greenhouse effect and warms the planet. Another quiz. So, which of the following is a greenhouse gas? 1, 2, 3, or 4. So, have a go at figuring out which is a greenhouse gas. Okay, good. Option number 4. Yep, so it's actually all of the above. So greenhouse gases may be a result of natural occurrence or human activity. So these gases include carbon dioxide, methane, which is CH4, water vapor, nitrous oxides, and ozone. So fluorinated gases are also considered to be greenhouse gases as well. So they act like a heat-trapping blanket, making the Earth habitable for humans. However, human activities have increased emissions of greenhouse gases into the atmosphere beyond what the Earth can physically support, and this has resulted in climate change. So here is a nice figure showing what the greenhouse effect is. So we've got solar radiation coming in and hitting the Earth through the atmosphere layers. In both, it's the same amount of solar radiation that's hitting the Earth. On the left, we have a normal level of CO2, which was observed in that hockey stick figure for like the last 800,000 years, minus the most recent part. And here we have rampant CO2, where we have a lot of CO2 in comparison to what the planet can support. So we can see on the left-hand side, we've got less heat trapped in the atmosphere and more heat escaping into space, whereas on the right hand side we've got a lot of heat trapped in the atmosphere and less heat escaping into space. Okay, have a go at writing in the chat just a few, like if you could just put a couple of points for each question. So firstly, what does anthropogenic mean? Because climate change is mainly caused by anthropogenic influences. Secondly, what do you think are the biggest contributors to climate change? And thirdly, what are the biggest impacts of climate change? So just have a go at putting in the chat, just type in the chat options 1, 2, and 3. Have a go at that. Okay, good, good. So we're getting what anthropogenic means. Yeah. Yeah, okay, brilliant. Yeah, so this means that climate change is mainly caused by human influences or yeah, basically caused by influences that have been created by humans. Okay, biggest contributors to climate change. Yeah, burning of fossil fuels, certain countries, industry and agriculture. Excellent. Yeah, all of these things. And then let's have a go at question number 3. Reduction in biodiversity, sea level rise. Yeah, sea level rise. Again, for number 2, transport and electricity production. Very good. Okay, great. So let's explore these in a little bit more detail. We'll have a think. Yeah, release of CO2 from the oceans. Excellent. Destruction of habitats. Good, good. It's nice to see everybody participating. Okay, brill. So let's have a think about some of these responses and what the contributions and impacts of climate change are. Extreme weather, very, very good. Changes to weather pattern, also great. Okay, so what contributes to climate change? So burning fossil fuels like coal, oil, and gas for electricity, heating, and transport releases a lot of CO2. And the CO2 released from burning fossil fuels has a distinctive chemical fingerprint. So we can tell the type of CO2 in the atmosphere that has specifically come from burning fossil fuels because of the chemical fingerprint that it has. We also have contributions such as deforestation, so cutting down forests, etc. Agriculture, lots of livestock, cows producing methane, and certain farming practices, and industrial processes like cement production and chemical manufacturing. So which of the following is not a consequence associated with climate change? Let's put a poll up. 1, 2, 3, 4. So hopefully this is getting you to just reiterate and rethink about the motivation behind why we might need to do research in these areas. Okay, excellent. Yeah. So the following decrease in widespread migration of people across the globe is not a consequence associated with climate change. Climate change will actually impact the amount of mass migrations occurring for affected societies because extreme weather events such as droughts and floods continue to occur across the globe, and more locations are becoming uninhabitable for people to sustain livelihoods there. And so there's actually going to be an increase in mass migrations, which will to be able to continue to avoid the impacts of climate change for these people for as long as they can. So some of the impacts of climate change today. So at 1 degrees above pre-industrial levels, we have things such as the Himalayan glacier melting rate has doubled since 2000, which is affecting water supplies for 1 billion people. Ocean acidification, so the oceans have already absorbed 30% of our carbon emissions, which affects thousands of species. We're experiencing extreme rainfall and floods. So the UK extreme rain has increased by 16%. And we're also already seeing human migration. So 22.5 million people from 163 agriculture-dependent countries are forced to migrate. We also have this important statement at the bottom that we all need to halve emissions by 2030 and reach net zero by 2050 to limit warming to around 1.5 degrees by the end of the century. But as we saw in that graph earlier, we're already at we've already had a 2024 as a year with greater than 1.5 degrees above pre-industrial level warming. So let's look at what will happen if we do get to this 1.5 degree figure. So we're going to get a lot of sea level rise, up to nearly 0.5 metre by 2100. And we will have heat waves. So deaths in London increased by 65% per year. 15% of global population exposed to deadly heat waves once every 5 years. We'll also have a lot of vector-borne diseases where the conditions for the diseases to spread are more prevalent. And we'll have biodiversity loss as well, where we're losing coral reefs and vertebrate and plant species. If we go beyond 1.5 degrees, I don't even really want to think about what the impacts will be, but it's very important that we face what will happen. So things such as 99% of the coral reefs will be completely obliterated. We'll have lots and lots more wildfires. You've probably seen a lot in the news about the increase in wildfires within recent years. That will become even more drastic. We'll end up with crop yield change, which could lead to starvation of millions of people, complete loss of species, and incredibly high amounts of sea level rise and melting glaciers. So it is really quite devastating, which is why it's super important that we need to research and focus our attention on making sure that we're protecting our planet and reversing some of the damage that we've caused. So, talking about research, my research was actually to do with looking at how sea ice fractures. So we have two pictures here showing sea ice, and you can see lots of melting, you can see lots of cracks in the sea ice. It's not like one big solid piece anymore. and this is a consequence of global warming. So this is like this motivates the type of research that I was doing for my master's project. So let's look at the importance of sea ice. So sea ice deformation holds much responsibility for the condition of the global climate, and its role is pivotal to understanding and preventing the rapid and deadly changes associated with global warming. At its maximum extent, sea ice covers approximately 10% of Earth's oceans, and thus is a really big factor for consideration when making global climate predictions. The sea ice cover, consists of irregularly shaped ice sheets, which are called floes, Floes, and they're separated by cracks or leads. The network of cracks within a floe forms when sea ice fails under imposed stresses caused by the wind and ocean. So sea ice is important for climate regulation. So sea ice has a high albedo, which means that it's very reflective. So it reflects a lot of the sun's radiation back into space, meaning that it isn't absorbed by the water. It reflects instead of absorbing. When sea ice melts, however, if there's lots of global warming and sea ice is melting, it will expose a darker ocean water, which absorbs more heat and propagates a feedback loop, causing further warming. It also will affect ocean circulation. So the ocean circulation is very dependent on the amount of salt that's in the water. When sea ice is made or formed, it leaves behind salt in the surrounding water, increasing the salinity and density of the surrounding water. This drives something called the thermohaline circulation, which are the global ocean currents, which helps regulate climate across the planet. Obviously, most of you will have seen lots of documentaries about why sea ice is important for polar life. So it provides an essential habitat for polar bears, seals, walruses, penguins, and microorganisms as well that form the base of the Arctic and Antarctic food webs. As I said briefly earlier, sea ice is also a very important indicator of climate change because it's extremely sensitive to temperature changes, making it a key indicator of global warming. And declining sea ice is one of the clearest signs of a warming planet. Also, there will be a lot of influence on weather, so changes in Arctic sea ice can alter jet stream patterns, potentially influencing weather extremes in mid-latitudes. So how do we actually study this? So we're going to introduce a topic called rheology. So what actually is rheology? Rheology is the branch of physics, so it's a topic, and it deals with the deformation and flow of matter, especially when it's non-Newtonian, as in it doesn't follow Newton's laws very easily, and it's mainly a flow of liquids and the plastic flow of solids. So I'm going to introduce some of the key concepts behind rheology, and starting with some things that you've done at A-level and then extending it a bit beyond that. So to study sea ice, we want to study the relationship between the forces and deformation for each case. So for each kind of deformation, we will introduce a quantity called stress, which characterizes the strength of the forces causing the deformation on a force per unit area basis, which means force divided by area. When stress and strain are small enough, we often find that the two are directly proportional, and the proportionality constant is known as an elastic modulus. So when stress and strain are small enough, they're directly proportional and they follow something called Hooke's law. So simply put, this means that the harder you pull on something, the more it stretches, and the more you squeeze it, the more it compresses. So the stress and strain are proportional to one another. The proportionality of stress and strain under certain conditions, Hooke's law, is only really valid under certain conditions. So it's not valid all of the time, it's only valid up to a certain limit. So it's not really a law because it's only valid over a certain range, but it's quite convenient to study small stresses and strains. Okay, we also have the Young's modulus, which is given by tensile stress divided by tensile strain. So the tensile is important here because in a minute we're going to look at something slightly different, an extension of this. So tensile is where the force is perpendicular to the edges. So if you've got something here, you're going to be pulling on it or pushing it, and it's going to be the force is perpendicular to the edges of the material. So there's different types of deformation. So we've already talked about compression and tension, the squeezing and stretching. We can also have something called bending, shear, and torsion. So the simplest behavior to understand is obviously the stretching of a bar, rod, or wire when its ends are pulled or pushed, and you can apply forces of equal magnitude but opposite directions to its ends, and we say that the object is in tension or in compression. What is actually very interesting for sea ice is this process of shear. So, what do we mean by shearing? We don't mean this. We actually mean this. So, if you look at this diagram, we have F parallel, which is a tangential force to the surface. We have A, which is the surface area of this face. We have X, which is a certain displacement, and H, which is the height of the whole material. So shearing is actually when forces of equal magnitude but opposite direction act tangent to the surfaces of opposite ends of the material. So one part of the object is being pulled one way, where another part of the object is pulled the other way. So what happened initially was for the tensile stress and strain, we would have two forces of equal magnitude and opposite direction acting perpendicular to the surface. And now we've got them acting tangentially to the surface. So the figure shows that one part of the object under shear stress is displaced by distance x relative to the opposite face. So we can define the shear strain as the ratio of the displacement x to the transverse dimension h. So if I put this equation up, here we go. Yeah, so we have shear stress divided by shear strain. So for Young's modulus, it was tensile stress divided by tensile strain, and now it's shear stress divided by shear strain. And for tensile, we had F perpendicular here, and now we've got F parallel because it's a tangential force. So for a given material, the shear modulus is usually 1/3 to 1/2 as large as the Young's modulus, Y for tensile stress. So the concepts of shear stress, shear strain, and shear modulus apply to solid materials only because we need the shape to be a definite shape, an object to have a definite shape to be able to be deformed. However, these concepts can be applied to things that have a bit of plastic flow or things that have a bit of liquid properties, which we'll get onto in a minute. So here is a very nice diagram, which I took from an A-level revision website called Save My Exams, which is a very good website if you're revising for your A-levels. And we can see initially we have Hooke's law where there is stress and strain are directly proportional to one another, which means that there's this linear relationship. So suppose we plot a graph of stress as a function of strain. This graph will hopefully be familiar from your A-levels, and if Hooke's law is obeyed, the graph is a straight line with slope equal to the Young's modulus. It ends at a point called the limit of proportionality, and the stress at this point is called the proportional limit. After this, there is no direct proportionality between stress and strain, so Hooke's law is no longer obeyed. The elastic limit is the point before which you remove the load. So when you take off the load or the stress or whatever, you take it off, there will be no permanent deformation, and the stress-strain graph will gradually retrace its steps back to the origin along the same line from which it came. So for elastic materials, which obey up to the elastic limit, the deformation is reversible. The forces are called conservative, so the energy put into the material to cause the deformation is recovered when the stress deforming it is removed. So the material up to the elastic limit shows elastic behavior. When we increase the stress beyond the elastic limit, we enter a plastic region. So the strain continues to increase, but now when we remove the load, the material does not come back to its original length. So the length at zero stress is now greater than the original length. So the material has undergone an irreversible deformation and has acquired what we call a permanent set or a plastic flow. So here, just to make it really simple, what we have is an elastic region, linear proportionality, followed by either brittle, where it snaps basically, there's a catastrophic failure, or we have ductile region followed by stationary plastic flow, where we can keep stretching this, like, say if it was a plastic bag, we can keep stretching this plastic bag and it's like a stationary flow where it keeps extending. And we have elastoplastic materials, which are materials that exhibit elastic behavior followed by plastic flow. Then something happens and they go back into the elastic regime following the stress and strain profile. Then they go back through and they go into plastic flow. Then they can repetitively cycle through elastic and plastic flow. So let's get a diagram up to show this. So this diagram was taken from a paper that I published and to do with my master's research. And elastoplastic refers to a type of material behavior that combines elasticity and plasticity. So basically it shows how materials deform when they're loaded. So in elastic behavior, the material deforms under stress but returns to its original shape when the stress is removed. And in plastic behavior, after a certain point called the yield point, the material deforms permanently even when the load is removed. So elastoplastic materials actually first deform elastically with reversible flow, and then yield and deform plastically with irreversible flow. And they follow a stress-strain curve that reflects both phases. So this number n is actually the cycle number. So we repetitively shear, which means that we repetitively apply stress tangentially to different faces of an object. So we're shearing this material over and over again, and this n shows the number of cycles of shearing. So 0 is where we've sheared it 0 times, 1 would be we've sheared it 1 time, 5,000 we've sheared it 5,000 times repetitively. So you can see initially we have 0, which is the dark blue, and that, can you see, has got a straight line. This is stress on the y-axis, and this is strain on the x-axis. So we've got this straight line, which shows that initially we've got elastic behavior because we've got proportional relationship between stress and strain. So initially we've got this elastic behavior, but then you can see as the number of cycles increases and the colour tends towards red, we move away from this elastic behavior and we start getting a more bendy profile, which eventually culminates in this red region, which is a region of stationary plastic flow. So basically it will keep extending and keep reversing in these dimensions. Another branch of what we need to look at to understand the problem of sea ice is with amorphous materials. So examples of amorphous materials are shown on the screen. So we have things like glass, amorphous metals, some polymers, amorphous ice. And amorphous materials include soft solids such as emulsions, colloids, gels, granular materials, and molecular glasses. Amorphous materials appear solid at rest and will only flow if sufficient load is applied to them. An amorphous material is one that lacks a regular repeating atomic structure. So unlike crystalline materials, which have an ordered lattice, like table salt or quartz, for example, amorphous materials have disordered atoms or molecules. So you can think of it like the difference between a brick wall, which is crystalline and structured with a repeating pattern, or a pile of rocks. It's still solid, but now there's no long-range order for the pile of rocks. So amorphous materials represent this pile of rocks, this solid but no long-range order. Amorphous materials actually behave differently from crystalline ones. They often don't have sharp melting points. They soften over a range of temperatures. They can be more flexible and less brittle or more resistant to crack propagation. Their thermal and mechanical properties differ due to the lack of a repeating structure, and unlike crystalline solids, they lack order in the arrangement of their constituent microstructures. So understanding their rheological or deformation properties is thus a major challenge. So typically, They behave elastically at low loads and then yield plastically at larger loads, which will hopefully start you thinking about why I introduced the topic of elastoplastics and why I'm now introducing amorphous materials. But you may be asking, how are amorphous materials and elastoplastics actually related to sea ice? How is it actually all related? So sea ice is primarily made of crystalline ice, which is specifically hexagonal ice, which is the common form of solid water on Earth. But under certain conditions, like rapid freezing or high pressures, amorphous ice can form. So what actually is amorphous ice? Amorphous ice is a form of ice, but it doesn't have long-range order. So it's unlike regular crystalline ice. It's still ice, but it doesn't have any long-range order. It can form when water freezes very quickly, and it prevents the molecules from arranging into a regular lattice. So three main types exist: low, medium, and high density. While most natural sea ice is crystalline, amorphous characteristics can still be relevant because sea ice contains pockets of brine, which is liquid salty water that is trapped inside the ice. And these microenvironments can undergo supercooling and rapid phase transitions, which might locally create disordered or amorphous-like structures. And in compressed sea ice, such as at pressure ridges or where sea ice might crack and break, pressure can alter the structure of the ice, which potentially induces local structural transitions that are less crystalline. So this all links to how amorphous materials deform differently than crystalline ones. So now what did I actually do? How did I model this? What did I do? So we've talked about elastoplastic and what that means. So now let's introduce elastoplastic models. So we've talked about several of these things. So hopefully you've done some mechanics in your A levels, and you've got a bit of knowledge about elastic theory because we talked about stress and strain and elastoplastics. We've talked briefly about what amorphous solids are. And you'll also know a bit about what rheology is, which is like the deformation and flow of matter. So this is introducing that. So elastoplastic models follow this pattern. So there's, as I said before, it's elastic flow with linear stress and strain relationship, followed by plastic flow. So it's elastic, plastic, elastic, plastic, over and over and over again. So what happens is we've got an elastic deformation occurring. We keep stressing something, and the strain is proportional to the stress. So it's elastic, it's going to reversibly go back to what it was before. Then all of a sudden, we have a dislocation or a disordered movement happen in the structure where it now snaps into a different shape, which is the plastic event. So it can no longer go back to exactly how it was before because it's moved into a different space. Then the stress, which was all contained in this, which had built up in the elastic deformation, is then released and transmitted to molecules all around it. So to explain this a little bit more thoroughly, we can have a well analogy. So these three figures represent a well. Each one is a well. The first one is a well initially. The second one is after some time where stress has been applied. And the third one is a completely new well. So the orange circles represent the stress elements. So initially they're distributed within a certain width. We then apply stress and push them along the x-axis. And when they've reached the conditions of the edge of the well, which means that it's reached enough energy, it can then hop into the new well. So this is a way that we model it, basically. So I created some code that modeled n different particles and them increasing in stress, and then imposed a condition so that once it reached the edge of the well, after it reached that and those conditions were fulfilled, it could then go into a new well where it would start elastically deforming again. So if you imagine between the first and second well is the elastic deformation where they're all moving along the x-axis. The plastic deformation is where they reach the edge, they fulfill certain conditions, and they hop into a completely new position, a completely new configuration in a plastic way. So let's have a brief look at some results that we found to do with sea ice. So I theoretically studied the dynamical process of yielding in cyclically or repeatedly sheared amorphous materials. And I used a thermal elastoplastic model. So I used an elastoplastic model that had temperature involved as well. And I used a particular type of rheology model, a particular deformation model. And we can see, you don't need to take in all of the details of these graphs. The main points are that we have, this is maximum stress per cycle. This is the number of cycles, like we were talking about on that really pretty rainbow figure, where we shear and each one is a cycle. So we have a initially slow accumulation of stress, and then all of a sudden we have a plastic event. So this is where the stress redistributes, like in that figure from earlier, we have the stress redistributing, so the stress decreases very sharply. And these are the actual fracture events of sea ice. So we can see where the shear stress is decreasing very rapidly. These are the points where the sea ice would be fracturing. So we can see over a long time after the inception or beginning of shear, there's low levels of damage. And then this slow fatigue suddenly and without warning gives way to catastrophic yielding and material failure. So these steep slopes up here, so we've got the maximum standard deviation of stress, which rapidly increases as well as the same as the maximum stress per cycle decreases. So these are some really interesting results which predict exactly when the material, the sea ice, will fracture. And obviously this is motivated by the climate change that we talked about and the fact that we want to have a really good understanding of exactly how sea ice works, when it fractures, etc. So just a little conclusion. So some nice polar bear pictures, and we talked about how the extent of sea ice has a really large effect on the evolution of climate. So it's really important to research it and fully understand exactly the mechanisms behind how it works and how it's breaking up. We learned that sea ice is an amorphous material, and it's a solid that lacks a regular repeating structure. We learned about things such as rheology and elastoplastic models. And we can model sea ice as an elastoplastic, and we can predict its fracturing using computational tools. So here are some references, and then I have some further resources to learn about this topic if it's of interest to you.